Alright, I'm going to start out this video the way I usually do by looking at Chuck Penson's excellent book, Heathkit Test Equipment Products. Flipping to Chapter 3, which is Digital Frequency Counters and Multimeters. Heathkit's first digital product using digital electronics was the IB-1102 frequency counter, which was good for up to 15 megahertz. And it came out in 1970, so designed in the late 1960s. And it was just made for a couple of years. Came out in the Christmas catalog of 1970. It was obviously not very fast. It used all TTL components and used a single circuit board and Nixie tubes. Shortly before it was discontinued, Heathkit came out with the IB-1102, which was a frequency scaler allowing slower frequency counters to be used to read higher frequencies. So it would basically just divide down the higher frequencies to something that the slower ones could display. In 1972, when the IB-101 was discontinued, Heathkit came out with two new frequency counters. The IB-1100, which was twice as fast as the slower original one, up to 30 megahertz. And this was more of a consumer level product. The case was cheaper, the functions more basic, but it still gave you some bang for buck. And it was also sold and promoted in the catalog side by side with that frequency scaler. The same year they came out with the IB-1101, which I have a video on, which was a bit more sophisticated, a bit more professional in its build quality and presentation, etc. And that was good up to 100 megahertz. And they made that for about 3 years. At the same time that came out, the IB-1102 was available, and it lasted for longer in the catalog. It lasted up to 1977. And this was just an incremental improvement over the 1101. It had more digits for one thing. And it also had a little better accuracy, and so better accuracy, better resolution, and it would go up a bit faster. It went from 100 megahertz to 120 megahertz. So there's more shielding in here, more care towards being able to handle the higher frequency range in a more stable, professional, reliable manner. And this is the frequency counter, which is the subject of this video. 1 year after the 1102 came out, Heathkit introduced the IB-1103, which went up to a 180 megahertz and had some more user adjustability, more control over how the counter did its job. It has push buttons for time base and a multiplier, and a couple of input jacks. This one used a different feature than the other ones before it, in that it used a phase lock frequency multiplier. Now the book jumps to the digital multimeters, but keep in mind that the 1102 and the 1103 were both discontinued sometime in 1977. We have to jump over all these digital multimeters. In 1975, the IM-4100 came out, which was a jump from the older technology Nixie tube displays to LED displays. And this was 30 megahertz, so not a very fast one, more of an entry-level one. And I have one of these, by the way. I still use it from time to time, even though I have better ones on my bench. In 1977, Heathkit came out with this family, the 4110, 4120, 4130, which differed in number of inputs and their frequency range In 1980, those were junked and replaced by the 2410, which looks a lot like the 4100, but it's 225 megahertz instead of 30 megahertz, so much more capable. And then the IM-2420, which was 512 megahertz, and the same year the 2400 came out, which was a handheld 512 megahertz frequency counter, which I also have a video on this one. And that's pretty much the end of the Heathkit frequency counter lineup. So now let's get to the subject at hand. Okay, here's the artifact. This came to me from an eBay seller who had obviously taken good care of it. It doesn't really have any blemishes on it. Even the paint on the case is in good condition, so I won't need to repaint it. The window has got some small blemishes, but nothing too horrible. And there was a little dust on the tops of the switches and things, which I've already cleaned up. Obviously I've got the case top and bottom removed. Just giving it an exterior overview here. This is the main counter board here. So we start out with counter ICs, and then we go through latch ICs that store the data, and then we go through ICs that actually drive the Nixie tubes. These are all Fairchild parts. These are Texas Instruments. And one thing that's rather interesting here is, for some reason, Heathkit didn't want to bother with socketing pins that weren't being used. So you can see the left pin there and the right pin there are not in sockets. And these are the same kind of things Heathkit was crazy about using in this period of time in the early 70s. I think that's when this came out. Late 60s, early 70s. They were using these Molex pins that came in strips with a header that you had to snap off after they were soldered to the board. There's no actual housing. So I don't know why they tried to economize like that, but they did, and it just looks like something's missing, but it does work. Anyway, and they've upped their game here. Other lower end meters like the IM-1102, which was Heathkit's first digital multimeter, and the IB-1102, which was Heathkit's first digital product, period, and their first frequency counter, and then the subsequent 1101, which is the lower end model of this 1102, they had to put a light shield behind the Nixies so you wouldn't have ambient light coming through the front window, going past the Nixies, lighting up stuff on the circuit board or whatever, and then bouncing back out and being visible to the user. So you have this light shield. On the lower end models, certainly all the ones I've had a chance to look in, they didn't do anything. It's like an afterthought, and they just had a cardboard thing that you'd cut out from a piece of cardboard they would supply, and then fold it and like scotch tape it in place. It's kind of kludgy. And certainly all the ones I've worked on, those have either been missing or they're falling apart, and I've 3D printed new ones. But this one, it's actually part of the structure. There is a piece of sheet metal that comes over here. It's bolted to the side frame, comes over, and it has the holes for holding two tiny little incandescent bulbs, the leads of which go to this terminal strip, and then from there on with wires. And then it bends out, goes behind the Nixie tubes, bends over, and does the same thing, holding two more indicator bulbs, incandescent bulbs, again with a terminal strip, and then it makes a bend and is bolted to the the side frame over here. And there's sort of a rubber or plastic, you can see it running along the bottom there. That's so that the metal here doesn't short out any foils on the circuit board, because it's essentially touching the circuit board. Anyway, so that's the essence of what's on that front board. Now there's a transistor here, for example. I should point at it with my screwdriver. And over on this side there are a couple of transistors, and those are the things that are providing a drive for the bulbs on the left and the bulbs on the right, so that digital logic can turn the transistor on, then the transistor sinks the current that's required by the bulbs. If the lower end models, and maybe slightly older models in this series, used small neon bulbs instead, so they had to be energized by the 90 to 100 volts from the high voltage power supply, and then you needed the transistors because the digital logic couldn't handle such high voltages. Anyway, on here, those are the drive transistors, and everything else is done with the 3 rows of ICs I've already talked about. This is the power supply area. It's dominated by the power transformer, and there's the line fuse down there on the bottom. Really hard to get at place. They could have done so much better with that. I think they should have put it, up here or something. It would have been much better. Anyway, and then the back side of the line cord socket, and then the back side of the 2 5-volt voltage regulators that are bolted to the heat sink. Unlike the IB-1101 that I already have a video on, which has the same kind of IC but only one of them, and it's just on the back sheet metal of the case, where on here there are 2 of them, and they're not in parallel. One handles one part of the circuitry, another one handles another part. They both produce 5 volts, and so they're running as independent supplies for different parts of the circuit. And then the actual power supply circuit board is here, and then going around we have 2 more plug-in boards. There's room for 3, provision for 3, and I think the next model up from this did use that extra bay for an extra circuit board to go in there. Anyway, we have the front end circuit board. This would be the part that does input limiting, attenuation, amplification, impedance matching, Schmidt triggering for waveform shaping. All that kind of stuff would be on this board. And then the timer board, the one that generates the high frequency that's used, divided down for use as the gate signal, which opens and closes and allows input signal to go into the counters or not. That's handled on this board. The front panel is very simple. There are 8, if I turn the lamp around you can probably see them, 8 Nixie tubes, and there's a decimal point right in between 4 Nixie tubes and a decimal point, 4 more Nixie tubes. The decimal point does not move on here. It always stays in the same position. Then we have our on-off rocker switch and the kilohertz megahertz rocker switch, and the one and only input, a BNC jack. There are no other operator controls. Everything is automatic other than selecting the range and of course turning it on. On the rear there's not very much. First off, there's an input here which is for an external clock. So you can use the internal oscillator or the external oscillator, and there's a slide switch for determining which one you're going to use. Normally you'd have it on the internal, but even though it's got a pretty good, stable, accurate oscillator, there may be situations where you want even better performance out of this counter, and you wish to use a laboratory grade clock signal that you can bring in here, and then just move the switch to external, and then part of this circuit is not used. The part that's the clock, really the part in the blue housing here, gets replaced then with the signal coming in here. There is an oscillator adjust. It's factory calibrated, but you can see there's an adjustment there, hole through the rear of the case, and then a screwdriver slot inside the blue housing. And then on the front end board there's also a level adjust, which is back in there somewhere. It's kind of hard to see what it goes to. Once again, the two voltage regulators, they're marked with Heathkit part numbers, not the original manufacturer numbers. And then the type of connector that was widely used on Heathkit test equipment at this period of time, but only for a few years before it was replaced by, different types. It was a short love affair, and lots of other companies, Hewlett-Packard and others, used the same connector for a while. It wasn't a very good connector, but for a while it seemed like that's what everybody wanted to use. And then of course we have the model number and its power capabilities in terms of frequency and voltage and how much wattage it uses. And there's you have to hardwire this for the line voltage. There's not an internal switch. You have to wire the transformer one way or another. And so there's a graphic on the rear panel that says wired for 120 volts and also wired for 240 volts, and you put the product sticker over the one you're not wired for, so it covers up. As far as I can tell, this is a kit. It does say IB-1102. Pre-assembled or factory assembled test equipment from Heathkit had a different number, so you could tell that it was factory assembled. But I have to say that the quality of the assembly on this is first rate. Very neat, really nice solder joints. Every component lead bent just perfectly. Very professional job. If I have to say so, I'd say it's the same kind of job I would have done when I was building Heathkits. As I always thought, if I'm going to build this thing, I'm going to do it right. The main counter circuit board does not plug in, it's just bolted to the chassis. But the input board, the clock board, and the power supply board are all unpluggable. They're all on plugs into chassis connectors. And then on the back side, or the bottom side, it starts looking like an old tube radio, where you would expect to see a circuit board, and instead it's just hand wired. But of course there aren't that many connections here. It probably didn't really justify a circuit board for this. Of course we do have the bottom of the counter circuit board. We have the power switch, and it does have the piece of cardboard. You have to have a piece of cardboard in every Heathkit product, I think. And that's not to say other manufacturers didn't use cardboard as an insulator as well. There's the kilohertz megahertz switch. It's got two halves. The top half is the part that actually tells the logic which position the switch is in, and it changes the way the counter board works. And then the other half is what actually operates the two lamps on the front panel that indicate kilohertz or megahertz. I'm not real fond of the way they did this, and it drove me nuts initially, because when I would operate the switch, the front panel indicator would turn on kilohertz or megahertz and would show me that, but the display did not change. I said, well, it's lying to me. The switch is moving, it's indicating that I've moved the switch, but the circuitry doesn't know I moved the switch. At least the important circuitry doesn't know. And as it turned out, there was a fault in the switch here. Not actually broken, but must have had some gunk got into it, and the front half of the switch was not making contact. So a couple applications of deoxit seems to have fixed it up. I hope that it remains fixed. I actually assumed there was probably a fault on the board. Sometimes you get these Heathkits, and because they're not factory tested and people assemble them and make mistakes, sometimes they don't realize they made a mistake, and the mistake is just there, and they say, oh well, and they move on. Maybe they never use it because of the lack of functionality, or maybe it works well enough to satisfy them, and then they don't care about the part that doesn't work. Or maybe they built the product and they're too ignorant to realize it doesn't work properly. Some people don't read manuals very well and don't follow the instructions, and if they did, they probably wouldn't have those problems. Anyway, but I thought there might be a problem on the board, so I probed it with my oscilloscope and found that the ICs were all doing what they were supposed to be doing, but the signal from the switch was not getting there, and the input to the relevant IC was not changing states when I moved the switch. So I thought, well, maybe there's a problem with the connector, so I checked it here and rang it out. The wires, only 2 wires going up to this switch, and they were making connection. And then I turned it off and just put an ohm meter or a continuity checker across the switch, and voila, the switch was not working. Anyway, so we have the power cord here, or the wires from the power cord jack coming over here, and they run up and go to the power switch. And then the leads from the transformer are brought over here to the power supply connector. And then this is the other half, the power supply board connector. And there's one lead that goes off to service those 2 large voltage regulators. And then coming out of there are the 2 wires that are the voltage regulated sides from those. And they don't need a ground lead because the chassis serves as the ground for everything. Except for the one black wire, which has to go all the way around here to the switch. So they could have just had a lug there and a short jumper going to the switch to get the ground, but instead they ran a wire all the way from the board that's using the signal all the way around to the switch and all the way back to the board. Just a little bit more wiring here. Power supply wires coming down and going to the first circuit board here. You can see some ferrite beads are on there, 3 places, and another ferrite bead here. A few more wires that are coming from rear panel things. A couple of wires between the boards. Not really very much has to go between them. At some point you have to take the input signal and get it to the next board, and at some point you have to take the clock and get it to the next board. And then of course they go from there and just run straight across and go straight into the counter board. And pretty simple wiring, not much to it. One thing of interest here is this one flying component. It's a 100K resistor, and it just picks up from a point on the circuit board that has 5 volts, because the incandescent bulbs on the front panel are running off of 5 volts, just like all the digital logic is. And it just goes through that flying resistor and goes to the kilohertz megahertz switch, and thereby switches the 5 volts to one wire or the other. And these are the ones that go around and go to the small terminal strip and then to the kilohertz and megahertz indicators on the front. These 2 boards just simply unplug, but the power supply board, for whatever reason, has a screw securing the top of it. So I have to unscrew that to get it out. There's a better view of the connectors, and those are by Molex, a venerable connector company that's still quite in business. And the kit actually is supposed to come with an extender board, because it's hard to work on these boards when they're down in their metal cages, which is there for shielding purposes. Once you start getting into the higher frequencies, shielding becomes more important, and that's why they have individual chambers for these boards. It might be that Heathkit just thought, you know, where these boards are going to go, they're in these little chambers. They can't really move very much, and if they did, it's not going to hurt anything. Whereas this one here has considerable power on it, and if it came loose and rattled around in there, it might possibly cause a bigger problem. So maybe that's why they put the screw on it. So this frequency counter uses 4 different power supplies. Actually 5, I guess, if you want to count the 2 5-volt supplies as 2 supplies instead of 1. So there's a diode bridge that uses these 4 large diodes, and because of so much circuitry in here that's early TTL, not low power TTL, you know, very beginnings of TTL logic, they're pretty power hungry. And there's also a certain amount of ECL, that's emitter coupled logic, chips on here for the very front end and some other critical places where regular TTL at that time could not keep up with the speed requirements of this 120 megahertz capable frequency counter. And the ECL uses a lot of power, and it always uses it, not just during transitions. That's one reason why they have 2 large voltage regulators for the 5-volt logic supplies. Anyway, so you get the front end rectification, and then 2 electrolytic capacitors for filtering, 2200 microfarads each. The originals were 2000 microfarads, and I should say that other than just some general cleanup and fixing that one switch on the front which wasn't making good connection, the only other thing I had to do to this is I replaced these 3 electrolytic capacitors. There are no other electrolytic capacitors anywhere in the product. It was working with the old ones, but when I removed them or pulled one lead off and did an out-of-circuit ECR test, the ECR readings were pretty bad. Not horrible, but pretty bad, and I don't like to have defective components in the products I restore, so I found that these Illinois capacitor, which is a part of Cornell Doublier, or whatever they call themselves, had some axial capacitors with the same kind of ratings and the same physical size, which is something I can't always get. So they go in there very nicely, they look good. So you get your filtering, and then the from there the filtered DC goes out through some of these connectors and goes to the 2 voltage regulators. And there is another diode bridge over here, lower power and therefore smaller diodes, that rectifies another secondary on the power transformer. And then it's brought around these 2 transistors, a larger one and a smaller one. These are 2 resistors, a Zener diode, and this capacitor. Actually, I think there's 2 Zener diodes. Yep, the other one's right down here by the connector. So what they're doing there, and it's exactly the same circuit as the IB-1101 that I already did a video on, they take the rectified somewhat higher voltage because it's providing the analog circuit plus and minus, like plus and minus 15 volts, something in that order. So it's got a voltage somewhere above 30 volts, but it doesn't have a lot of current requirements, so it only has a 100 microfarad filter capacitor. That's all that's needed with such a low loading. And then that jumps all the way over to the other side of the board, where you have essentially a Zener reference circuit. Not exactly a regulator, but it does use the Zeners to get the voltage at approximately what you want it to be. It's using 2 Zeners of the same voltage in series, So if these are like 16 volts each, you end up with, you know, the appropriate 32 volt Zener regulation voltage. And normally for that you would have a current limiting excess voltage dropping resistor going from the power source to the Zeners, but those can get hot, dissipate a lot of energy. And so what they have here is a 2-transistor circuit. It's a current limiting circuit, and it normally doesn't do very much, but as the load changes and the voltage is moving around, the Zeners conduct more or less, and when they're conducting more, then you've got more current going through this 2-transistor current limiting circuit, and when it gets to the point where it's too much, it starts increasing its own resistance dynamically, so you're not throwing away unneeded power. It's just a better way of doing it. And the one that's handling the actual pass current is this larger one, and then this one is the one that actually detects the current going out of that supply, and a voltage is dropped across it, and once detected, then that starts modifying the way this other one works so that it changes its how much it's conducting. Finally, you need the high voltage supply for the Nixie tubes, and that's done with just 2 components, this fairly large diode and this large capacitor. Comes off a 3rd secondary winding, and you might think it would go through the diode to get half-wave rectification and then the capacitor for filtering, but what it's really doing is going through the capacitor in series, and then the diode goes from that point back to the other side of the secondary. I'm trying to remember exactly what it's called. I think it's called a Villiers circuit. I'll verify that and put a caption in the video. It's really like the front half of a common voltage doubling circuit. And what it results in is a positive only waveform that's essentially like a clipped sine wave, and it's all above ground. So it's like it's rectifying it in the sense that it's raising the AC voltage to be all above ground, but it's not changing it to a steady state current or anything like that. If it was normally rectified, you'd have, with one diode, it would be halfway rectified. You'd have half the waveform of the sine wave, then nothing for half the period, and then another pulse, and so on. What you get with this is you get the whole wave going up and down with just a little bit at the bottom clipped off due to the diode action, and all the actual power is going through the capacitor in series. And you can only do this for very low current applications, and also if the load doesn't care that the output is pulsing that much. Anyway, so let's take a look at the back of this. Oops, clumsy. It's not even a plated circuit board, it's just raw copper. And I thought it might have some shellac over it, but it does not. But very neat soldering on this. Whoever did this was doing a good job and knew what they were doing. Used just the right amount of solder. The one thing I didn't like is that they bent the leads like flat over the board and then didn't cut them as closely as I would have. And about the extender board, I actually interrupted myself and went off on a tangent. Now I'm coming back trying to finish what I was saying before. So I was saying that these guys, because they're down in these shielded chambers, it's hard to work on them. You can't get at the components very well. You can hardly see them. And if you want to make connections with a meter or oscilloscope probes to the backside, you can't even hardly see it. You can see this one a little better. In the other version of this, where there's an extra card in here, you wouldn't be able to. So what they had, and it's part of the kit, and it's in the instruction manual, it's a board very much like these, but simpler, and it has the same kind of connectors on one side and the other. And I guess you can't keep it in. A lot of test equipment that used extender boards had an extra bay in there where you could stick the extender board. And maybe it's possible to stick it in here somewhere, I don't know, but there's no obvious place for it. And then what you would do is you'd plug the extender board in there, and then it would have the top of the board about here with a new set of connectors with pins on it, just like those, and then you'd plug the board that you're trying to work on, and it would be up here instead of down in the hole. I actually wanted to create an extender board for this because it's missing. It did not come to me with the rest of the product. The problem is that I verified with Molex they don't have anything like this anymore. And they haven't been able to tell me what the part numbers are, even though I gave them good photos and dimensions and everything. I could say, could you check your old catalogs? We don't have them anymore. So I'm still working on that, because I would like to build an extender board so this thing is complete. And just in case I have to work on it some more, it'd be nice to have. Okay, here's the rear of the clock board. This one does have plating, and it's double-sided. And then looking around at the front, yeah, clearly a double-sided plated foil circuit board. And it does have a silk screen on it, but no solder mask. Those were not all that common in the days when this product was made. So here we have a bunch of Fairchild counter chips, and these may be ECL parts. I haven't checked yet, but I wouldn't be surprised. And then you've got some TTL logic. This is all Texas Instruments stuff. And this one's Texas Instruments, but it also has the Heathkit part number on it. Actually, I think all these do. Sometimes these parts would have only the Heathkit part number. Sometimes they would have both the original and the Heathkit part number. These do appear to all have Heathkit part numbers on them. Anyway, so the job of this circuit is to generate a high-frequency clock, which then gets divided down to be used as the gate signal, which admits pulses from the input to the counting circuit. That's the main thing. Now this one, unlike the IB-1101 that I looked at already in my previous video, which had its own oscillator, just a couple of inverters on an IC, a couple of resistors and a capacitor, a very simple oscillator, still pretty good in performance, but not as stable as you might like to have for a higher end instrument. So what they have here is some sort of temperature compensated assembly, the internal circuitry of which they do not reveal. But I do not believe it's a crystal oven. The better counters would use a crystal oven oscillator, so the crystal that was the basis of the whole clock would be kept in a temperature controlled chamber. And the problem is usually you want to keep it warm and keep it not colder than that or hotter than that, and then everything would be calibrated at that stable temperature. Well, I don't think this one here has an oven. There don't seem to be enough leads coming in and out of it. And as far as I can tell from the literature I found, it doesn't mention a crystal oven, but it is a temperature compensated crystal of some kind. So it's better than what was done on the slightly lower model in this series. Otherwise, there's not really very much on the circuit. Oh, one thing I wanted to mention. All the boards in this that plug in have two sets of 6, including the power supply board, but both of these boards that are dealing with higher frequencies also have like a ground plane connector, and it uses two of the same kind of connectors in series with each other, and then instead of the normal connector like one of these down here, it has this post which screws directly onto the chassis, and if you don't trust that for having a good electrical connection, then there's a solder lug on the back side of it which has a wire going directly to a ground connection. And that pin fits through both of these, and I think the idea there is they could have just done it with another pin on here. There's enough spares, I think, but that post is taller than the other pin, so it makes a ground connection first before the other connections are made. To unplug this board, I have to get rid of this coaxial connector that runs from the input jack through a hole in the chassis, and then it comes down into the chamber and comes up with a RCA plug that plugs into an RCA jack on the circuit board. I can't actually get it out all the way until the board's lifted up a little bit, and then it can be disconnected the rest of the way. Okay, there's the front end board. It's a combination of transistors. There's quite a few over here, a whole bunch of them, and I'll talk about that when I talk about the schematic. But basically there is a differential circuit for the very front end where you've got several transistors each doing a different thing. That's three of them. You can see 1, 2, 3. And then there's a common current source transistor that's used by both halves, and then another 3 transistors that are duplicates or in a duplicate circuit to what the top 3 transistors are for. And then all these components around it support that. And over here is an op-amp that's used with this. And again, I'll get into it with the circuit description, but essentially what's happening there is it's a large differential amplifier. The input signal feeds into one half of it after some front-end conditioning, which I suspect is being done around here somewhere. And then it goes into the differential amp, and that provides the sensitivity, the gain, things like that. But it does not provide the pulse shaping. That's done by a Schmidt trigger IC, which is one of these. And so you're driving one half of the differential amplifier, one input of it, with the input coming from the RCA jack, and then the other side is monitored by the op-amp and reaches back around and drives into the other input of the differential amp. And that's just sort of a feedback circuit where it's looking for a particular amount of signal, and it's going to adjust the sensitivity up and down until it gets the signal it expects. So that is essentially an auto sensitivity circuit right there. And then we've got a few more odds and ends, but you know, you're cleaning up the signal and then making it available for use by the other circuitry. That's about it. Alright, all of my repairs and cleanup have been completed on this frequency counter, and I've also spent many days going through the circuit boards, wiring, verifying wire colors, connection points, nomenclature, component identifications, connections on the circuit board, all that, and marking up my schematic. A lot of errors in the Heathkit schematic and other documentation. I'll be able to put out a new schematic and documentation package, as I often do with these, which will be in much better condition than the original documentation. So having said that, let's just give a quick demo. As usual, when you turn it on, it takes a couple of gate cycles before you get a meaningful number. So you just get some garbage for a couple of gate cycles. Now I get 0, so it's a legit number. We've got the gate indicator going on every second. And we're currently in kilohertz mode, also indicated by the switch. I have my function generator set up here. Currently it's at 1 kilohertz. I'm going to take it down to 100 hertz. And I'm going to turn the function generator on. And we get 100. This is on the left side of the decimal points. That would be 1 kilohertz, so 0.1 is 100 hertz. And as usual with these things, they're only good within 1 digit, least significance. So you expect the rightmost digit, the least significant digit, to maybe be off by 1. That doesn't mean the instrument's out of calibration. And I just realized that the Nixies are slightly wonky in their sockets. Let me straighten those guys up again. That's a little better. So let's go up to 1 kilohertz. And there we are, 1.000 kilohertz. And I'll go to 10 kilohertz. Let's go to 100 kilohertz. And if I go to 1 megahertz, we're sitting there just a notch under 1 megahertz, 999.994 kilohertz. And I'll go up to 10 megahertz. And it's still within the number we can get while still in the kilohertz setting. This counter can go up to 120 megahertz, and my function generator peaks out in the low 20 megahertz range. Let's put in a more interesting number. Let's go to 20 megahertz. We're almost ready to roll it over. So let's go up to 21. And I can't overrange it here because this is not like a 3.5 digit display where it can only go up to a 1. It can count up to full value on every digit. So 25 megahertz is the highest I can get my function generator to output, but we're obviously very close to the right number here. So let's switch over to megahertz. The decimal point will stay in the same place, the indicator will move. And now we're in megahertz mode and we're reading 25.000 megahertz. So that's working just fine. Take it down to 24, 23, and notice the gate indicator does not light up at this point. That's because it's gating so fast it would just either look like it's always on or always off, so it just doesn't even turn on. 22, 23, I'm sorry, 21, 20, 19, 18, 17, 16, and with such a short gate time, the update is instantaneous. Alright, let's put in an arbitrary number here. 3, 4, 5, 6, 7, 8 megahertz. Oh, come on. I'm screwing up here. I'm going to put in 1, 2.3, 4, 5, 6, 7, 8 megahertz. And we do have that 1, 2, 3, 4, and it would be 5, but it's off by the least significant digit. But this is low enough to show it in the kilohertz range now. Give it a second or two to catch up. And 1, 2, 3, 4, 5.59, that would be 6, and then after that we're a little bit off. So I can boost this up to get a good number. Let's see, after the 0.59. That's about as close as I can get it within the resolution of my function generator. But obviously this is a perfectly working unit at this point. Nice clear display, pretty good accuracy. Alright, I've had to replace the feet on the bottom. They were just about falling off. So I've cleaned the bottom and I put new 3M bump-on feet on in the positions indicated by the manual. I noted that the original ones were placed a little bit outboard from where they should have been. I think somebody just eyeballed it. These feet are bigger than the originals, but they're the same style, same manufacturer, and this is what I put on all my restorations of bench equipment or bench top equipment. And there's this fish paper. I had to check the manual to see where this was supposed to go, and it's supposed to go as the case bottom and towards the rear, so I've marked that on here. All the circuit boards that come close to the bottom are here, and most of the exposed wiring is here, especially the higher voltage wiring is here, so obviously they did one little extra insulation in that area. I've reassembled the handle on there, and I should point out, I think I've kind of given this the short shrift in my other videos. For example, on the IM-102 and the IB-1101, they all have this same kind of detent system, which is a little kludgy, not as nice as a professional meter would use, but still better than a lot of them. It just has on this one side a keyed to the handle. In other words, the handle is keyed to this lug, which can turn, and it has 4 flats, and then there's a leaf spring there, piece of spring steel secured with 2 screws. And when you try to turn it, it deflects the spring so it doesn't want to turn until you get it to a certain orientation, which has to be 90 degree or 90 degree increments. So there's no in between if you want it to lock. But then it pretty much stays in that position. You know, it doesn't want to have other positions, but they're still useful positions. And also, I should point out that with this early series TTL in here, and the ECL, where they're, none of this is ECL, but there's ECL in these boards, those all tend to get pretty warm. It's very power inefficient, I should say. A lot of dissipation in those parts. So you can hold your hand over these boards and, you know, keep them from getting cold on a chilly day. This whole thing's a big heat generating engine with no ventilation. Still, these have a good reputation for longevity, and presumably the elevated temperatures are not enough to cause premature failure of the components. They are designed to run pretty warm. There's a bit of a trick to getting the case halves back on because they fit behind this strip, which is held on with a couple of screws to the inner chassis, and because the handle wants to spring inwards, it tends to push these strips inwards, but they need to be outwards in order to allow these to drop into the grooves. So at some point you're pretty much obligated to kind of like get a ruler in there or something and try to pry it in. Then it'll drop in the rest of the way. And then finally screwing these down. And it seems like the case always wants to spring out a little bit, so it's really a two-hand job. One hand to pinch the top and half case halves towards the center, and the other one to turn the screwdriver. Okay, here's the beauty shot. And here it is on my wall of vintage test equipment. Until I put it there, I thought it was the same size as the IM-102 and the IB-1101. I think the the IM-102 and the IB-1102, that's the subject of this video, probably are about the same size, but certainly the IB-1101 is a substantially smaller case, although in the same design. Alright, let's take a look at the Heathkit manual for the IB-1102. This is a reproduction manual by manualman.com. I was not able to find an original, but Manual Man does a really nice job. My only complaint is that they tend to use binding that's a little small for my tastes. So sometimes when you get towards the middle of the manual and you're trying to turn pages, they might bind a little in the middle. They haven't had many complaints, but I don't like it, so I tell them to send me the manuals printed but not bound, and then I put my own binding on it. In this instance, they made a mistake and punched it for the type of binding they use, not the wire binding that I use. But luckily I still have my old plastic comb binding machine and was able to put on my own binding. So, assembly and operation manual. It's got several different chapters, building one circuit board at a time, followed by building up the chassis. Many pages dedicated to that. So 2 pages of table of contents. Introduction. The model IB-1102 Heathkit frequency counter is a compact, lightweight, rugged digital frequency counter. The basic functions and uses of this instrument are like those found on other high-quality frequency counters. Many features make the counter convenient and easy to operate. 8 cold cathode display tubes, those are Nixie tubes, an overrange lamp, a gate lamp, and 2 range indicator lamps provide an easy-to-use display. The display accuracy is assured by modern digital techniques and a temperature-compensated crystal control clock. Notice that this is temperature-compensated, not a crystal oven like the best frequency counters use. Well, there's probably even better ones that, you know, use much more expensive techniques, but as far as benchtop ones, usually the crystal ovens are the best ones. This is not one of those. This is temperature compensated, so what they actually have in there is a module with a voltage controlled oscillator, and then they'll have a temperature dependent element like a thermistor in some sort of voltage divider arrangement or network, and that changes the voltage dependent on temperature, and that feeds the oscillator and compensates for drift in the crystal according to temperature changes. So anyway, it's more stable than just a simple oscillator that's not temperature compensated. A high impedance FET input circuit presents minimum loading to the circuit under test, and the automatic triggering level feature provides simple hands-off operation. The counter with its two regulated power supplies can be operated either from 110 to 130 or 220 to 260 volt 50-60 Hz AC power source. Lightweight and reliable plug-in integrated circuits and plug-in circuit boards minimize and simplify maintenance. The detachable test cable and line cord and the 3 detent position bail-like handle make the counter completely portable. The unique bail handle can be used to position the counter at a desirable viewing angle. Because this is a more complex build, it has a paragraph here about don't open up the various packages and intermix them. Open up one parts bag at a time according to which subassembly is going to be put together next. And then there's the usual assembly notes. Starts out with the power supply circuit board. That's the simplest one. So small bill of material. And building up the circuit board on 1, 2, 3 pages, and then you're done with that. The time-based circuit board, parts diagram and bill of material. 1, 2, 3, 4. Yeah, 4 pages of assembly on that one. Then the input circuit board. This is the most complex, although not the largest. It's probably the most difficult one to build. So you have no parts diagram here. They basically refer you back to earlier parts diagrams. And it has really about 1 page of bill of material split between 2 pages. Then right off the bat it's starting into the assembly. But there is on a fold-out the parts identification diagram. So that was a little odd, but that's the way they did this one. Sometimes Manual Man will adjust the arrangement of fold-out pages. So this isn't necessarily the way the original Heathkit was. So anyway, 1, 2, 3, 4, 5, 6 pages of assembly. Then the counter circuit board, which has probably the most parts. Parts pictorial and parts list, it all fits on 1/2 of a page because there aren't many components. It's just a lot of the same ones. Just a handful of resistors, couple of transistors, I guess total of 4. And then transistors and integrated circuits. Well, just integrated circuits. There's only 4 different kinds of IC, but there's quite a few of them. And when it says 366 here, that's referring to this Molex type of IC socket that Heathkit was in love with during the time these came out. I don't know if they just thought they were cheaper or good enough or what they were doing. They're generally reviled by people these days, but they worked. I've never had a problem with these not working on anything that I've restored, the old equipment. They do work. They're just a pain to set up and they seem cheap. Anyway. So 1, 2, 3, 4, 5. I've got a couple of notes to myself that are stuck on here. I'm trying to come up with some parts to make an extender board, which is the next chapter. The extender circuit board, bill of material and parts diagram, half a page, 2/3 of a page. This one has some brackets, so there's diagrams on that. Some thoughts I've been sketching up for how to make one of these. My frequency counter did not come with the extender board, nor is there a place to store it inside the case. And that's probably why everybody I've seen who has one of these is missing the extender board. And each of the circuit boards on this is stuck inside of its own shielded container part of the or section of the chassis, and you can't really work on them when they're down inside these recessed areas. And so if you do need to work on one while the power is turned on, you need an extender board to lift the plug-in boards up high enough that you have them outside of the chassis and therefore can work on them. Extender boards are actually quite common with anything having back planes and so on, because if you have a bunch of circuit boards plugged into a rack, the surrounding circuit boards will block access to the one you're trying to work on, so you need to extend it up above the other one. Same idea here. And Heathkit actually had a lot of different extender boards for many different products. Unfortunately, they're all different, so you can't use one on the other. I've been in contact with Molex to see if they could tell me the part numbers for these things, sent them diagrams, illustrations, and photos, and they just bombed on it. They apparently don't keep company archives, which is shameful. Because if I could find out the part numbers for these things, I could probably find somebody who has new old stock and build up some of these things. Anyway, then the chassis, a lot more parts on this, 2 pages of bill of material, and then your basic. There's something about this paper that manual man used on this particular manual, which the pages just feel slippery to me. Have a hard time turning them. So basic chassis assembly, lots of pieces. Oh yeah, and then the parts diagram. More detailed illustrations. More parts diagram. Fold out. More assembly. And you start mounting in circuit boards that have already been fabricated, like the main counter assembly circuit board. And then various things are mounted, like fuse holders and so on. And the IC voltage regulators on the back panel. The various slide switches, AC power cord socket, BNC connector, all have very nice diagrams. And then we start wiring it up in the voltage regulator and fuse and power socket and oscillator select switch areas. Then we start putting the pin connectors into the chassis for the various plug-in circuit boards and mount the power transformer. And wiring up the wires from the power transformer and some items on the back panel. They're giving you just a little bit at a time here so you don't get confused with all the wires that end up being in this space. And then wires from the various plug-in circuit boards to the counter circuit board, which does not use plugs and is not unpluggable. It's the only one of the 4 circuit boards which is not unpluggable. And then there's a wiring harness which is factory made, and we install that into the chassis. Then we have to figure out which voltage this is going to be used at and wire up the transformer one way or the other depending on the voltage. Here we install the shield plates between areas where different circuit boards will be installed, and we put a bit of a fish paper up against the chassis because there's a cable that plugs into a connector on the circuit board that goes in here, and it would be possible for the back side of the connector to short against this chassis shield plate and ground out the input, so that's there to prevent that. And then there's a light shield. Now if you've seen my videos on similar vintage equipment like the IM-102, Heathkit's first digital multimeter with Nixie tubes, looks very much like this product, and the IB-1101, which is the slightly earlier, slower frequency counter. They all had cardboard light shields, which I was kind of thinking were kind of kludgy. I ended up making 3D printable replacements for them and show those in my videos on those two products. But this one, it's a little more professional, a little higher priced, and a little later. And it's like, well, now the light shield isn't an afterthought. It's an added expense. Folded up piece of sheet metal painted black, insulated along the bottom so it doesn't short out the circuit board, and it has lamp holders for the 4 incandescent bulbs for the overrange, gate, megahertz, and kilohertz indicating lamps. Wiring up more of the AC power stuff and the front panel lamps. Some notes about plugging in the Nixie tubes, which I don't think they ever call Nixie tubes anywhere. They just call them display tubes. And then mounting in the light shield to the rest of the chassis. Installing the Nixie tubes right up next to the light shield. And then wiring up the 2 switches on the front panel to the existing wiring harnesses. And then plugging in the 3 plug-in boards, the power supply, the input circuit board, and the time-based circuit board. And don't forget to plug in the shielded cable coming from the front panel input jack, which plugs into an RCA connector there, and that's what the fish paper is behind once this board is plugged in. And here's a fold out, and there's a little diagram here for connecting the other end of that shielded cable from the front panel BNC jack. Making up the cheapo test cable. Test cable assembly. And then initial tests and a diagram showing how you can clip on with a resistor that's included to do a self-calibration and test. And that's part of the initial test. It needs to get a signal from somewhere to measure, and even though it may not be calibrated yet, by using this system here, it just taps off the internal oscillator and then feeds it back in and measures itself essentially. And again, it's not calibrated, so the number may not be accurate, but at least you can see that it's working. Then final assembly, putting on the side rails on the chassis, mounting the handle / bail, putting a large piece of fish paper on the bottom of the chassis that protects from shorting out all those wires that are on the bottom of the chassis mid plate. Putting feet on the bottom half the case. Shows how to put the top and bottom of the case on. A diagram with voltages for the various circuit board connectors. And then just a rear view. Then the calibration. And then front panel displays, indicators, switches, jacks, tells what everything does. Then the operation and application notes. Various tricks for measuring things, including making a little coil that you can wave around next to parts of a radio circuit, for example, rather than making a direct connection. The in case of difficulty section, and here's how you would use the extender circuit board to get a board up above the chassis. Troubleshooting chart. Specifications. Frequency range 1 Hz to 120 megahertz. Gate time 1 millisecond, or 1,000th of a second, or 1 second. Accuracy is plus or minus 1 count, so the least significant display digit could be plus or minus 1 from the actual frequency, plus or minus the time base stability. So if your time base is off, then you've got that, plus the error of plus or minus 1 count. Readout, kilohertz or megahertz with a fixed decimal point. 50 millivolts maximum sensitivity. DC coupled. Impedance is 1 mega ohm in parallel with 35 picofarads. Trigger level automatic. Maximum input is 120 volts RMS. It's protected by diodes on the input circuit, but that is susceptible to frequency. So it can handle 120 volts per this chart at low frequencies, but once you start getting up around about 20 megahertz, the amount of voltage you can apply to the input drops off precipitously until you get up around 100 megahertz, and then you can only have a maximum of 20 volts input. Then we have the circuit description, several pages of that. Some chassis photos, circuit board x-ray views. One perverse thing they did on here was, for example, the input circuit board is shown the way I would consider to be proper, with the front and rear views as if you just flip the board around that way and everything else stays the same. Whereas this one, it's a top to bottom view, so they flipped it that way to look at it. You think that they could have just been consistent and picked one way or the other, because all these boards are the same size. I think it's like they had different draftsmen doing it. And yeah, then the big counter circuit board is also flipped this way. Some voltage charts for various circuit boards showing key points that you can probe. Identification chart for transistors and the Nixie tubes. The diodes. And my much enhanced integrated circuits. I've made lots of notes in here by poring over the original manufacturer's data sheets. And I pasted in a table. A lot more markups. It's hard to see them the way I'm showing them, but they're there. And then the schematic diagram is on a great big long fold out. Kind of accordions out. And then I think the notes that usually went in this area are blown up as one whole page here. So they're the notes on the schematic diagram. And then finally the replacement parts order forms that would always be there, how to reach customer service and repair service, and we're done. Alright, let's take a look at the schematic. I'm going to use Heathkit's version instead of my own, and I don't plan to resort to much in the way of sketches, although I probably do a few. I'm going to be winging it in that regard. The schematic is organized into the power supply, the time base circuit board, the fairly elaborate input circuit board, and the large counter circuit board. And I'll pretty much handle those one at a time. The power supply is really conventional, and indeed it's nearly identical to the one I covered in my most recent Heathkit video on the IB-1101, the lesser version of this one. So we come in with the power cord, the ground connections brought immediately to the chassis, and this schematic symbol is used here as ground, but with a couple of exceptions, especially where things that need to be grounded are not in contact with the chassis. Everywhere else, the chassis is used as the ground connection without a separate wire. If I were to do this, I would change the symbol to a chassis ground type of symbol. Trying to figure out how to get rid of the shadow I'm getting there. Maybe that's a little better. So we have a power switch up here and the fuse. Pretty simple. And then the transformer with dual primary windings. They're wired in parallel for 120 volt use or in series for a 240 volt use. Then there are 3 secondary windings. The first one is about 8 volts RMS, and it's given the full wave bridge rectification with the negative side of the bridge connected to ground, and then the positive side getting a couple of filter caps to smooth it out, and then actual voltage regulation is done by a pair of UA309s or LM309s. This is like a precursor to the 7805. It's a 5 volt regulator. Because of the current draw of all the ICs in here, and especially the ECL ones, or just the large quantity of TTL ones, it's divided up by 2 voltage regulators. This one handles the time-based circuit board and the counter circuit board. So pretty much the bulk of the TTL loads. And then this one handles the input circuit board, which is ECL logic primarily. And it probably doesn't hurt to have it on its own supply to avoid noise from all the digital logic here interfering with the analog section, although this is for the digital part of the analog section. Then the next winding is about 37 volts RMS, also full wave bridge rectification, and the result is I don't know why there's a jumper here. I think it's just for convenience on the circuit board. But there's a small filter cap. Current demand is low, so a small value of capacitance is enough to smooth out the ripple. And then this schematic, this is actually an error here. In the IB-1101, the same circuit is used, but these 2 transistors are flipped upside down, so this one is up here and this one is down here, and I can see almost where they gave it to the draftsman and said just do the same thing, but by flopping these transistors around, this capacitor is connected to the same place it would be if they were not flipped around. So this is an error in the schematic. This actually needs to be wired up to here. Anyway, this is an active current limiter, and it takes the place of the normal dropping resistor that there would be for a Zener voltage regulator. And again, this drawing is a little squirrely in the way things are located. These 2 Zeners should be viewed as being in series with each other, one above the other, just Zener, Zener. That would be the clearest, but they drew it like this. There's 2 Zeners of 16.1 volt each, and together, you get about 32 volts of reference developed across them. And of course, any excess has to be dropped up here, and instead of just using a passive resistor, it's got a series pass transistor. That's this one here. So normally this transistor is on, and the current flows through it from the bridge, goes through this small 68 ohm resistor, and then the 2 Zeners in series returning to the other side of the bridge. Now if the voltage drop across this resistor gets too high, which it would do if the current is excessive, then it starts, that resistor is actually across the base to emitter of this transistor, which is a smaller transistor, And once you get enough current going through here to develop enough voltage to bias this transistor on, then it starts conducting, and the current that was normally coming through this resistor to turn the base of this transistor on and therefore allow it to conduct, now some of that current is being stolen to go through this transistor, and to the lower voltage here is lower than the voltage here, so the current will go in that direction. And by stealing base current from this transistor, it starts to turn off, and therefore it increases its resistance, and it compensates for the increased current. Then the two Zehners do their trick, and you get the 32 volts across the two of them. But in between the two, between this one and this one, is ground, so that essentially produces a plus 16 volt and a minus 16 volt potential relative to ground. And those are brought out here as plus 16 volts and minus 16 volts. And those are used by the analog circuitry on the input board. The third secondary winding is about 75 volts RMS, and it's there for the high voltage supply that the Nixie tubes need. Never mind these jumpers. This is a single-sided circuit board, and those jumpers are just there to make it work as a single-sided board without having to do something else. This side of the transformer is connected to circuit ground, so you could think of this as the high side of the transformer. And these two components, this series capacitor and then this diode to ground, which is the same as putting it between here and here, pointing the other direction, because again this is ground. This forms a so-called Villard doubler circuit, and what it does is having trouble holding my camera steady. So if you've got your incoming AC waveform from the transformer, and it's like this, and it's 75 volts RMS, and since that's 75 volts RMS, that's going to be just trying to do it without the calculator. Let's call it 108, 110 volts, something like that, peak to peak. So from here to here, let's just round it off and call it 110 volts. Volts peak to peak. The Villard circuit here takes that and shifts it up. This is 0 volts here, and you end up with almost the whole waveform above ground, with just the little bit on the bottom clipped off, so it's not there, it just goes flat, and you miss the very bottom of the wave. But the rest of the waveform is there, but it's all shifted up above 0 volts. So you end up with a very highly pulsed DC voltage. It's not AC because it doesn't alternate polarity or go below ground, but almost the whole voltage is there. So let's roll that off and say we've lost 10 volts of the 110 volts from the clipping. So that would make that pulsing voltage from here to here about 100 volts. Voltage peak. And indeed, they're calling it a 100 volt source. They just don't mention that it's a highly pulsed source, not at all smoothed off. It's on for, about half the waveform, a bit more than that, and then off and then back on. So that's what's going on there. And that's okay because that's appropriate for something like the Nixie tubes. They do not need to have a constant, smooth voltage source in order to work in a satisfactory fashion. And by some estimates, having a pulsed voltage like that can reduce problems that Nixie tubes have, such as cathode poisoning, and that can make them have less problems over time. And sorry for the noise, my air compressor just kicked on downstairs. Alright, let's look at the input circuit board. There will be a little bit of splaining to do on this one. So the goals, as usual with frequency counter front-end circuits, is to condition a wide range of input voltages, which may or may not be above ground, below ground, above and below ground. You don't really know. And in addition to getting the levels coordinated, or conformed rather, so if you come in with a really low voltage, you need to boost it. If you come in with a really high voltage, you need to drop it, so that the resulting output of that is consistent and within the range of the digital logic that's going to work with the signal after that. So you have to get level shifting, and you need to get the wave shape such that it has a nice, clean, very sharp up and down signal. It can't be like a sine wave. So if you come in with a ramp signal or a sinusoidal wave or something like that, it needs to be conditioned to a square wave or a pulse wave with very sharp vertical transitions. So all those things have to be accomplished by this. Also, because this is a faster frequency counter, in its upper ranges it exceeds the ability of TTL logic of that time, before there was high-speed TTL and so on. So they need to use the emitter-coupled logic, ECL, which was intended for higher frequency applications and kind of petered out for the most part when TTL got faster. But, you know, it still is useful in very high-speed things like transition lines. ECL is a power-hungry logic family, but it has the advantage of the way it's structured internally, that it doesn't have the usual delays. For example, in TTL, the internal transistor structure saturates the transistors fully on, fully off, and so on, but that has a downside that once a transistor is saturated, it takes a little bit of time to get it unsaturated when you're trying to get it to change to the other logic state, and that results in it being slower than would be desirable in, you know, once you get into higher frequencies. ECL logic, on the other hand, always operates the transistors in essentially a linear mode, so they're not saturated, and therefore they don't have that time delay to move from one state to the other, so they're just faster because of that. So we have to convert the incoming signal to ECL logic levels so they can handle the higher frequencies, and the initial logic has to be done with ECL, and after that's done and the frequency's been reduced, then we can start reverting to TTL for the rest of the circuit. So let's get started. So we come into the input jack, BNC on the front. We go through the short shielded cable to an RCA plug, which plugs into the RCA jack on the input circuit board. So now we've got the signal into the input circuit. There's a loading resistor, 1 mega ohms, that establishes the input impedance at 1 meg. And then it has a diode clamp, one diode forward, one diode reversed from ground, and those are I don't know what an FD777 voltage level is, but let's just pretend like it's a silicon diode, so it would be 0.6 volts, 0.7 volts, somewhere in that area. So if the signal here gets to be higher than 0.6 or 7 volts, or lower than minus 0.6 or 7 volts, then one or the other of these diodes would conduct and essentially short to ground, and any excess voltage is dropped across this large resistor. So whatever you put in here, it's going to be reduced to a signal no more than 0.6 or 7 volts and no lower than minus 0.6 or 7 volts. So we've taken care of that first requirement to deal with what if the voltage input is pretty high. So now we've got that taken care of. Then we have to buffer it, and so there's an FET here. FETs have a very high impedance on their inputs, so that establishes that you won't load the circuit at all any more than this 1 meg is doing. This is so high impedance that from this point on, it's as if this stuff doesn't even exist as far as impedance and circuit loading would be concerned. So this is an impedance converter. This bipolar transistor helps the FET to do its job, and the result is a buffered version of what's here. And actually there's a bit of gain here, but it's fractional gain, so whatever voltage is coming in is actually a little bit lower when it comes out. Also, because this amplifier has got plus 10 volts on its positive supply and ground on its minus side, what comes out of it cannot be lower than ground. So now we've also got whatever came in here, if it was negative, it's 0, and if it's positive, then it's higher. So we've taken care of that aspect of it. And now we have a differential amplifier, that's right here, is drawn a little bit unconventionally. And that provides your amplification stage, followed by more amplification, and then followed by current drivers that again convert the impedance of this to a lower impedance for use in the digital logic downstream. And I've redrawn this a little bit so it looks a little more conventional. So this is your usual differential amplifier with 2 transistors, and the emitter side is common. This is, and because it's using PNPs, the emitters are on the top. Normally you would see this with NPNs, and the emitters are on the bottom, and those are tied together. But here the emitters are on the top, and they're tied together, and you can either feed that from a single voltage here, but in this case there's a constant current source. So holding this transistor's base at a constant voltage results in a constant current coming through here. There's only so much current that can come out. It can't exceed what's being put out by the constant current source. So some of the current's going to go this way, some's going to go this way, and then they eventually return to minus 10 volts down here by this path. The voltage that's dropped across this resistor, and really these two, but primarily this resistor, so the current that's going through here develops a voltage drop, and that becomes your voltage signal here. And likewise from this transistor, whatever current's going through this path develops a voltage drop, and that becomes your other output signal. A lot of times when you've got a differential amplifier, you're only looking at one of these two and you don't look at the other side. But the point here is that because it's a differential amplifier, it's looking at the difference in voltages from this base to this base. And you could drive one, or you could drive the other, or you could drive them both. Whichever one you're not driving needs to be held at some constant level. It could be an offset, it could be ground, it could be whatever. So if you've only got a certain amount of current going here, and this guy turns on more, that means more current's going to go this way. And since only so much current can come out of here, that means this side's going to be starved of current. This side will steal current by making it easier for current from the current source to go this way rather than this way. So simply increasing the conductivity of this transistor immediately means less current in this side, more current on this side means a greater voltage drop here, so this side goes up in voltage. Less current on this side means a lower voltage drop, so a rising input here means a rising voltage here and a dropping voltage here, and vice versa. So let's say we've conditioned our input to something resembling a square wave at this point. One of the differential amplifier outputs is going to look more or less like this, and because the other one's doing the opposite on the other output of the differential amp, it's going to be like this. It's going to be 180 degrees out of phase. However, the voltage levels will not be necessarily the same levels, so we have to take care of that. So now we've got what's called a cascode amplifier. Goofy name. It's been around for a long time. This is a cascode amplifier, and this is a cascode amplifier. Each is made out of 2 transistors, and these are designed to amplify at very high frequencies. It looks just like an emitter-follower amplifier, so if you took out this upper transistor and just had, you know, plus 5 volts, a resistor, and then this transistor, and then another resistor going to ground or some lower potential, this would work as an amplifier. It would be a common emitter amplifier, but in transistors of this sort, there's actually parasitic capacitances inside the transistor, for example, from the base to the collector or the base to the emitter. And at higher frequencies, those capacitors start looking like short circuits, and they affect the way the transistor works in a way that results in it not being able to handle the higher frequencies. So we need to cancel out that capacitance, and the way that capacitance works is called the Miller effect. So how do we get rid of the Miller effect? Well, one way we can do it is put this other transistor in here, which is not affected by the Miller effect. And I won't go into all the nuts and bolts on this, except the only reason this transistor is here is to cancel out the Miller effect on this transistor. And this is a common base amplifier. So the base is held at constant voltage, in this case circuit ground. And we've interjected it in there. Now, a common base amplifier like this has no current gain, but it has voltage gain. And so it contributes nothing to the ability of this circuit to drive current out of it, but by its presence and the way it behaves at higher frequencies, it cancels out the Miller effect of this transistor. So you can just view this as a frequency enabled, high frequency enabled emitter follower, and just think about this as that. But now, because we're taking the output from here, and this transistor has no ability to amplify current or really drive current, you need something to boost the current drive capability. So there's this additional emitter follower transistor sticking on the output of the common base transistor. So the 3 of these together are essentially what we wanted all along, just a way to take this signal and buffer it to go into the logic circuitry, and do so in a way that works at high frequencies. Now you may notice that this final amplifier here has got plus 5 volts on it, which is a logic level signal. Over here we had plus and minus 10 volts, but here we've got 5 volts and ground, so the output cannot be lower than ground, it cannot be higher than 5 volts. But otherwise it has the same shape as what's coming out of here. But the whole way this thing works is it's boosted the voltage signal coming out of here, the pulsing signal, it's boosted it, and it cannot go higher than plus 5 and lower than ground. Meanwhile, the other output of the differential amplifier, remember it's 180 degrees out of phase from the first one, goes through exactly the same kind of circuit. So we have now a cleaned up, voltage stabilized, square wave essentially, or some pulse wave depending on the wave shape of the input signal. And then we have its complement down here. Well, the first IC we have is this one up here. This is an ECL flip-flop. And I've redrawn it here. It's being used in a very simple way. It's not even using it as a toggled flip-flop. We're not using the clock signal. We're not using the normal input signal. All we're doing is using the set and clear inputs to the flip-flop. So we're manually forcing the output to flip to on, or forcing it to flip to 0 or off by use of these two inputs. And remember, these have their own voltage thresholds like all logic does. Above a certain input it'll be considered on, below a certain input voltage it'll be considered off. And remember, we've got those square waves here which are 180 degrees out of phase. Looking back at this, let's say this is the one that's applied to the set, and this is the one that's applied to the clear. So you get this one, and it's high, this one's low. Since it's low, it's not telling the clear to clear the flip-flop. This one is telling it to set the flip-flop. Then when you get to this part, it's low here, so the set is no longer telling it to set, but the high level on the clear is telling it to clear, and vice versa. And as a result, you're always telling the flip-flop to flip to one state or the other. It can't be both. And even if there's a little bit of misalignment on these signals, whichever one changed state last during this transition will be the one that affects the output of the flip-flop. I didn't draw the output of the flip-flop. There's the output. And since it's a flip-flop, it's called Q. So essentially what we've accomplished here is kind of a Schmidt trigger arrangement. This has done the final step of making sure that you have very abrupt outputs, that they don't go up at any kind of an angle when they change voltage states. They go very abruptly, and that's necessary for clean operation of the rest of the logic circuit. Now there's one more thing that's going on here. For this to work best, you really do want to have both voltage signals, the original one and the complement, have the same voltage levels, and that's not assured by the differential amplifier. So what happens here is we take these same two signals, that's these two, and in addition to driving the flip-flop, they're taken down here and fed into this op-amp. The op-amp is on a plus and minus 16 volt power supply, so its signals can go around quite a bit in terms of voltage. The capacitor across here makes this into an integrator. If you have a op-amp with a capacitor from its its inverting input to its output, that makes it want to integrate. By the same token, this capacitor on the plus input to ground has a similar effect. Basically what this is doing is it's taking the two signals, not their frequencies, but their amplitudes. So let's say that this signal is moving between 1 volt and 2 volts, so it's only got a 1 volt swing. And this one is moving between two voltage points that are maybe 3 volts apart. So you've got a 1 volt transition and a 3 volt transition. And that'll probably still work for the input of the ECL flip-flop because its thresholds are different from TTL in a way that would be advantageous here. But now we're averaging the one signal's voltage and we're averaging the other signal's voltage and then comparing them together and driving the output up or down depending on which one of them has the higher voltage. So if the one signal has a higher voltage span than the other one, and this is the one that has the higher voltage span, it's going to tend to drive the output lower. If the signal here has a higher voltage span than this one does, after averaging, of course, then it tends to drive the output higher. And that is what feeds into the other input of our differential amplifier. So it's acting as an offset. And it's also in kind of a feedback loop. The net result of this thing is all it's doing is adjusting, I would call it the sensitivity. I'm not sure if that's really what it should be called, but it's all I can think of calling it in a single word at this point. Many frequency counter front-end circuits have an auto sensitivity adjust, and I believe that is the purpose of this, that it's ultimately, in the big picture of this circuit, resulting in a sensitivity adjustment. Now we'll return to the original Heathkit schematic. Here's that same flip-flop. Its output is now, it now has the snap action we wanted, very sharp up and down, no ambiguity about it, and it's also at ECL voltage levels now. The ECL logic family has very different voltage levels for its logic than TTL does. And for these other ECL circuits to work, the voltages in here have to be ECL. Now there's one thing I want to mention here which confused me a little bit at first. Normally ECL is a negatively powered circuit, so it'll have a VCC, and normally you consider VCC to be plus 5 volts, you know, for TTL for example, and even lots of CMOS logic uses a VCC of 5 volts. You're just used to it meaning that. And then there will be a ground. So VCC and ground. But the ECL doesn't have a ground power supply pin. It has a VEE pin. And that is the lower potential of the voltage power supply, the lower side of it. But normally, and I'll illustrate it in a sketch here. So if this is ECL, it wants to have VCC. Come on, camera, focus. There. It wants to have VCC be ground, circuit ground, or 0 volts. And it wants to have VEE, I can't write today. It wants that to be something like minus, 5.1 volts or 5.2 volts. Somewhere in that ballpark. That's what you would normally power it from. But in this circuit, the chips are being powered from 5 volts, positive 5 volts on the VCC like you'd normally expect, and ground at VEE. Well, the chip doesn't know any better. It's still seeing about 5 volts across its power supply pins. It's just that the level has shifted from what you would normally have. And that's okay as long as the surrounding circuit works within those boundaries. And of course, like I said, the transistors here coming into the Schmitt trigger are putting out a positive only signal, and that would not be possible for the ECL if its power supply were really negative. So by raising its whole potential up by 5 volts, it suddenly starts working. But within this part of the circuit, all ECL, it thinks it's working between minus 5.1 and 0 volts, when in reality it's working between 0 volts and 5 volts. So we have to gate. I should step back and say that from this point on we are doing the counting function. So now, before going further, I have to just recap how a frequency counter works. So you have an input frequency and you've got its levels converted to logic circuit levels, and you're trying to compare that to how many pulses are happening in a certain period of time, and that is the frequency. And so typically what you have is a counter, a big digital counter, which I'll talk about later. It can accumulate a bunch of pulses and tell you how many pulses it's accumulated. So that's your quantity. And then you have to do it in a fixed amount of time, and that's called the gate. So there will be a very precise window of time that the counter is allowed to accumulate counts. And then that will be displayed, and then it'll be cleared, and then it'll do another count, so it can adjust to changes in input frequency. So the most important things are the time base, and I'll get to that later. This is what generates the gate signal, and the gate signal is the signal that determines how long the counter is allowed to count and accumulate pulses. And we already talked about the counter, and then you need the gate itself, and that is generated by a highly precision circuit that makes sure that gate is a precise length of time. If it isn't very precise, then you get a very inaccurate frequency counter reading. Common gate times are 1 second and 1 millisecond, or 1,000th of a second. As it turns out, on this frequency counter, you do have a 1 second gate and a 1 millisecond gate. It could be one or the other. And we open and close the gate according to the gate signal. When the gate is open, the input pulses come through and go into the counter. When the gate is closed, just as the name would suggest, the input pulses do not get through it and the counter stops counting. So we have a gate signal. I'll talk about how that's generated later. And it's TTL level. And we're going into an ECL circuit, so we need to convert the levels, and that's done here by a fairly simple 2-resistor circuit that adapts the TTL to the ECL voltage levels. And this would be more difficult if it wasn't for the fact that the ECL logic has all been raised to be above ground, as I already mentioned. This is the actual gate up here. It's an OR circuit. Now, Heathkit drew it in a squirrely way. They've shown it as a 3-input OR gate, and that isn't quite true. I mean, internally it's probably true, but from our perspective it isn't really. This pin 11 that's shown here, and it's going to ground, and here's another incidence of the same IC. It has 3 OR gates in it. It has a pin 11 connected to ground. And up here is the third part. It has a pin 11 connected to ground. What that really is a chip enable. So you can disable all 3 OR gates with an enable signal. And as long as you have that enable signal pulled low, then the OR gates are allowed to operate normally. And if you pull it high, then they don't work anymore. Well, they're all tied to ground, so that means they're all going to work. That makes this into a 2-input OR gate, and it has this signal, which is the gate pulse, and then it has this signal, which is the input frequency. And let's look what happens. This is another flip-flop here. It's actually part of the same one that I described that was acting as the Schmidt trigger. This one is being used in the same way. We're not really using it as a flip-flop. We're using it as sort of a memory device that can either be output on or output off. And that's accomplished by forcing it to be either set or cleared. So we get this gate signal coming in. It's been ECL level converted. And one of the inputs is tied to ground, which means that's ignored. And all it's going to do is the output's going to follow the input. So when the input is high, the output will be high. The input's low, the output will be low. But one thing this particular IC has is all of the outputs are actually differential. So it has a normal output that's shown here, and then it has a complementary output. So when this one's on, this one's off, and vice versa. And those are fed into this other half of the same flip-flop that was used here. In many ways, it's acting as another Schmidt trigger, although it doesn't really need to, because the output of this is basically the same thing, but it can't hurt. It can only act to clean up the output even more and make sure its output transitions are very abrupt, from low to high and high to low, very snappy outputs. So you've got no ambiguity in these things. The input signal is very tight, logically speaking, and so is the gate signal. And this output is logically high when the gate pulse is on. That's the time you should be letting things through, is when the gate is high, but look what's actually happening here. When the gate is high, and this is an OR gate, yes, the output will turn on here, but that clears it. That means the output here goes to 0. And then when this is low, when the gate is not on, logically this is a 0, but it's inverted by the complementary output, and now we have a logically high signal on the flip-flop set, which turns the output on. And what do we have with this? An OR gate can work like an AND gate if you consider the inversions. So we now know that the gate results in a low signal here, and when this is low, then all the OR gate is doing is looking at this input and copying it to the output. But when the gate is not open, then this will be a high level, and therefore the output is just always high. It no longer wiggles on and off with the input signal. So it's essentially blocking the signal. The counter can't count anymore when it's just being held high. So that's how the gate works. Normally you'd see an AND gate for that, but because of the inversions involved here, this functions like an AND gate. So the counter consists of 1, 2, 3, 4, 5, 6, 7 decade counters. That's a chip that can count from 1 to 10. But this is an 8-digit display. How does that work? Well, there's another decade counter over here made up of discrete flip-flops. All of these decade counters have essentially the same circuit inside them. You just don't see it because it's not shown. It's the internal functionality. And each one of these divides the frequency down by 10. So because it's a decade counter, when it counts up to 10 and resets, actually from 0 to 9 and resets, then the output signal is 1/10 the frequency of the input signal. So this is 120 megahertz maximum. Now it becomes a 1.2 megahertz signal maximum coming out of this first decade counter. Well, regular TTL can't handle 120 megahertz, or 120 megahertz. And if I said before it was 1.2, it's 12 megahertz coming out of this first decade counter. That's within the normal TTL frequency range. So we no longer need to use ECL with its higher frequency capability. Once we've got through the first decade counter, we can go back to good old TTL and use that. So because it's on the high frequency side of things, this first decade counter is on the input circuit board, which is also where all the other ECL stuff is at. So I won't go into all the details, but if you ever want to look up the guts of a decade counter in any data sheet, you'll see essentially the same thing. A bunch of flip-flops chained one after the other with some feedback from outputs to certain inputs and so on. And also there's usually an AND gate shown here, but when you invert the inputs and outputs of a logic function like an AND gate, it becomes an OR function and vice versa. Here we have these two flip-flops, and their Q naughts, their complemented outputs, are going into this OR gate, and then we're taking the inversion or the complementary output and going into the next stage. So since that's an OR gate where everything coming in and out is inverted, you could just picture that as being an AND gate without the inversions, you'd be coming off the Q outputs instead of the Q naught, and so on. So this is, again, just playing a logical game, and it's really, you have to think about it as being an AND gate. Anyway, so a classic circuit, decade counter, and the result is a signal coming out that's 1/10 of the signal coming in. And also we're keeping track of the count from 0 to 9. And that comes out in the form of the binary weighted A, B, C, D, the normal terminology. The A is the one that has a value of 1, B is the one that's a value of 2, C is a value of 4, D is a value of 8. And that gives you your binary pattern that you can use to represent whatever count is in here. Now I mentioned that everything downstream is TTL and everything here is ECL, so each of these outputs from the counter, the A, B, C, and D, needs to be level converted back to TTL. And that's what these transistors are doing. One transistor is operated by the Q output of a flip-flop. The other transistor is operated by the Q naught. So one or the other of those will be on. And in one case, well, they're both pulled up to here, but one has got its collector going to ground, and one of them has the collector going to ground through a resistor, so it's level shifted. And that's how we accomplish the level shift. So you have the A, B, C, and D signals coming out, and now they're TTL signals, not ECL. And they go on to the counter board. So because we have to think about this as a decade counter, that's our missing decade counter that we would have had in this position in the counter. So now that I've got past the front end circuit and diverted slightly into the counterpart already, just because of the physical location of the ICs, here's the time base. And again, the time base has one primary purpose, and that is to generate a very accurate gate signal. We start out with a crystal oscillator, and this is a TCXO, which means temperature compensated crystal oscillator. It's a module which goes on the circuit board, and it's powered from plus 5 volts and between there and ground, and then it has a TTL level output which is 4 megahertz. It's factory calibrated, but it can be recalibrated by the user, and that's 4 megahertz. And then we immediately go into a circuit which, even though the guts are not shown, it's connected as a divide by 4 counter. So you have 1 megahertz coming out of it. And then there's a switch on the back panel where you can select to use the internal oscillator, in which case that 1 megahertz signal goes straight through and back here. On the other hand, as good as this temperature compensated oscillator is, and I think I already said it, but I'll say it again, temperature compensated crystal oscillator is not the same as an oven, which is often called a crystal oven, where you're actually having a little heater in a insulated chamber with the crystal in it, and you're using the heater to keep the temperature at exactly the right temperature. You don't want the temperature going up and down because the crystal could change its frequency ever so slightly, so you hold it at a constant temperature. That's more expensive. This is not an oven crystal oscillator. It is a temperature compensated. So it just has a regular crystal. It is not heated to keep it at a particular temperature. It just is whatever temperature the ambient air is. But it has a temperature sensor in it, and the temperature sensor detects the temperature, generates a voltage, and the crystal is one that's a voltage controlled crystal oscillator, and so that correction voltage from the temperature sensor tweaks the frequency of the voltage controlled crystal oscillator such that it's always 4 megahertz. So anyway, so even with all that, this may not be stable enough for some more critical applications. So frequency counters almost always have an external oscillator input. If you have access to a more stable or accurate oscillator, you can put its signal into this jack on the rear. And this is another IC that's set up as a Schmitt trigger. It isn't really a Schmitt trigger per se, it's a different type of IC which just happens to have Schmitt trigger conditioned output. So it's actually like a multiple gate circuit followed by a Schmitt trigger followed by the output. So it's capacitively coupled to remove any DC component from the input signal. Then it's referenced to ground. It's actually held at a voltage that's based on this resistor voltage divider from 5 volts to here. So it's knocking the voltage down a bit and then applying it to the input where it is Schmitt trigger conditioned to get a nice snappy result, and then it comes back out, and if the switch on the rear panel is selected to external oscillator, now the signal goes through. Either way, you have a 1 megahertz signal at this point. I'm going to hold the camera with the other hand. The other one's getting a little tired. So what we have here is a bunch of decade counters, like I already talked about for the main counter circuit. It's actually the same exact IC, and there are 6 of them. Each one divides by 10. We're not using the BCD outputs the way we were from this decade counter and the way we are for all of these. We're not interested in seeing what the internal state of the counter is. We just want it to count up to from 0 to 9 and then reset and do it again, each time dividing by 10. So we come in, we divide by 10, and that 1 megahertz has been dropped by an order of magnitude. We do it again, it's been dropped by another order of magnitude, divide by 10 once more, it's another order of magnitude. That converts it into a 1 kilohertz signal, from 1 megahertz to 1 kilohertz. Now we have 3 more counters, each dropping an order of magnitude. So from 1 kilohertz to 100 hertz to 10 hertz to 1 hertz. So this is a 1 hertz signal coming out here. And because it started as a 4 megahertz signal and it's only been reduced through very accurate digital division, it's a very precise 1 second or 1 hertz signal. Now it's a square wave, and we know that if it's 1 hertz, then the point where the square wave is high is half of that, and the other half of the square wave is the other, so it's on for half a second and it's off for half a second. Now this frequency counter can operate in a 1 kilohertz or in a kilohertz mode and a megahertz mode. It's 2 different ranges essentially, and that is selected by the operator. And we have this front panel selector switch. It has 2 gangs, one of which provides a path from 5 volt power supply to ground, thereby turning on either the megahertz or the kilohertz lamp, so you can see readily which one you're in case you don't want to look at the switch itself. This gang of the switch just provides a way to ground this signal. It comes in and it goes to an input on this multiplexer IC, which is held high internally, so it's normally logic 1 unless we short it to ground. So when we're in the megahertz mode, we short that signal to ground, otherwise it's at logic high. And this multiplexer is really just a switch. It can go between this position and this position. It actually has a third position, but we're not using it. It's not connected to anything. Well, it's actually connected to this point, which is 10 kilohertz, but we're not using it in this circuit. Then there is these three inputs, A, B, and C, and those are just like the A, B, and C used in the decade counters. They're the first three bits of the binary pattern. So you have several options that you can get from the binary combinations, and those are determining which position this internal switch is in. Ultimately, is it aiming at the 1 megahertz signal or is it aiming at the 1 kilohertz signal? One or the other of those two signals get through, come out, and then go to the remaining three decade counters. That's how we can generate the 1 millisecond gate pulse or the 1 second gate pulse. That's where the gear shifting takes place, is how much of this division do we allow to affect what goes in and controls the gate pulse. Well, we're not done yet, because what we need is a 1 second gate pulse or a 1 millisecond gate pulse. And as I already mentioned a moment ago, this is a, if we're looking at this point, it's a 1 hertz signal, which means that here's a square wave. There's one cycle of the square wave. One of these is occurring every second. But what we really want is this to be 1 second long. That's only half of 1 hertz. A 0.5 hertz signal would give us a 1 second gate high period. So we need to do some more division. There's another flip-flop here, and all we're doing is using the clock input, and we're using it in the way that you can use a flip-flop to simply be a toggle. So when you get a pulse on the clock, the output turns high. When you get another pulse on the clock, the output turns low, and that repeats. Since it's been divided by 2, now we do have a gate signal here, which is 1 second long on the top and 1 second long on the bottom. The important part is the top. If, on the other hand, we use the 1 megahertz signal coming through here, we would have a higher frequency here, and the gate frequency after all these divisions would be 1 millisecond long instead of 1 second. So that's how we get that. So this is the gate signal coming up here, and it's a logic level signal. It can drive quite a few inputs to other ICs, but we also have to operate this gate incandescent lamp, this gate indicator lamp on the front panel. And just like the other lamps I talked about already, we have the 5-volt power supply through the gate lamp and then to ground through this transistor. Whenever the gate is high, it turns the transistor on. It provides the current path through the gate lamp to turn it on. So the gate lamp turns on whenever the gate signal is high. And then we go over here with the gate, we follow it all around, and we only actually have to drive one input, even though the output from that last flip-flop could drive quite a few inputs. All it really is doing is driving this one ECL gate up here, which then takes it from there and does the gating at the very beginning. So that's how the gate influences everything downstream. So the counting takes place during the period of time when the gate signal is high, but half the time the gate signal is low. What happens there? Well, that's the time when you're transferring the count into the display so you can actually see what the count was. And the timing is not happening at that point, so because the gate is closed, so whatever's in the counter is static. It just got up to that point and it stopped. This is a decoder, and it's working off this last decade counter. It uses its A, B, and C outputs to walk through several binary possibilities, one after the other. And the way they're connected together, you're generating a transfer signal, a clear signal, and a reset signal. One happens after the other, essentially. And the gate signal is one of the inputs to it, along with the A, B, and C from this decade counter. All we need to know here is that once the gate is done, the first order of business is to transfer whatever's in the counters into some memory so that it can be displayed. And that's why this transfer signal here comes out and goes across, and it goes into this driver, which allows you to fan out to many ICs. It gives it more current drive. And every one of the 8 memory ICs, which are really 4-bit latches, and they're calling them buffer storage here, but they're 4-bit latches, it's telling those to take whatever is in the counters, whether it's these counters or this counter, and take those data and stick it in the memory and hold it there. So then the counters can be reset and they can count up again, but during that time the display is only looking at what was held in the memory after the last transfer pulse. And at some point we have to reset everything. So let's look at that. We generate a reset pulse here. It goes through a transistor buffer. It goes over here. And first off, it goes over into this board, goes through another level shifter resistors, a resistor arrangement, just like we did for the gate. And that drives the clear inputs of these 4 flip-flops that together comprise the first decade counter. So that one gets cleared. And then we also branch off this reset signal and go into the counter board, where it's applied to all of the other decade counters to their respective clear inputs. So all of those get cleared at the same time. And then once we've done that, then we have to reset this circuit over here. And we do that by advancing the count again. And so that goes into the clear input of this flip-flop. I should mention that when this gate signal went away on its falling edge, you know, right when it finishes gating, the falling edge goes to this edge-triggered clock input of this flip-flop. And since the gate is over when this is clocked, that is what's clocking it, as I said already, I think, the output turns on, and that's saying, okay, we've done the part that needs to be done fairly slowly, and now we can do the rest of it much faster. So it reaches over here, and it goes into this multiplexer again. And what it essentially does is, even if we were in the 1 kilohertz position, it temporarily kicks it over to the faster position so that it gets rid the final stages of processing after the count is done are sped up. So otherwise you'd have to sit there and look at the display for a longer time when you're in the 1 kilohertz mode and you have the 1 second gate signal. You'd be waiting additional time for the rest of this housekeeping to take place. But it doesn't need to be slow. The only thing that needs to be slow is the gate. After that, the rest of it can go a lot faster. The part where you're transferring the data and resetting everything, that can go faster, and that's what this flip-flop takes care of. And by influencing the binary table in the multiplexer, it always makes sure you're in the 1 megahertz position during that housekeeping part so that it ripples through a lot faster. Let's see what else. So, yeah. So I think I've covered everything on that. And now we can look at the counter circuit itself. Oh yeah, there is one thing I forgot to mention. On here, it's part of what has to happen when you do the speed up. When this signal comes out of here to tell the multiplexer to shift in the higher frequency input. It also reaches up here and goes into this monostable. This is a one-shot kind of deal where rising edge here causes a pulse output of a certain duration, and that's selected by the resistor and the capacitor here, and that produces a pulse which goes into pin 7 of all of the different decade counters here. And that pin 7 is actually one of the presets in the decade counter. It has a pair of them, both of which will set the counter to 9. It's its highest value. Remember, it can go from 0 to 9. And so if you set it to 9, then the next pulse coming into it will flip it back to 0. So it makes it nearly done. The other input that sets to 9 is just left floating. And that's legitimate for this particular IC. It only really needs the one of them. So they're doing several things in here to speed up this thing finishing up what it's doing so it can overflow again and go down here and ripple this guy over to the other state, which then finishes this guy and cleans house and gets it all set up for the next gate pulse generation. So a lot of stuff goes on within each measurement cycle, and sometimes the housekeeping takes place in its own time. Other times it needs to be kind of pushed ahead and rushed through in order to get done in a reasonable amount of time, and that's what this stuff down here and this is all about here. Alright, we have our 8 counters. Remember that the one in this position is over here. And this is the least significant digit. It's the one to the right most end of the display. And the digit way over here is the most significant on the left side of the display. It's just convenient to show it flipped left and right in this case because the signals are coming from the left. We've transferred everything into these memory or latch chips, as already discussed. So let's take a quick look at the decade counters here. They're just exactly the same configuration as these down here, as I already said, looking back at it the other direction. And these also have 4 flip-flops in them. That's how they're built internally, just like these 4 flip-flops up here. And we already talked about how they're BCD outputs, showing what their count value is between 0 and 9. That gets transferred into the buffer storage or memory chips or latch chips, whatever terminology you want to use. The resulting BCD code, and here it looks like 5 bits. Heathkit was stupid. They're drafting guys, I tell you. Sometimes they needed to be reined in. They show the 5-volt power supply being right in the middle of the binary pattern. Who would do that? You know, ignore this, pretend like it's not there. It's just the ABCD 4 bits coming through into the decoder drivers 8 times. The decoder driver converts the BCD pattern, in other words the binary count of 0 to 9, and it converts it into a 1 of 10. So there's 10 outputs here, and each one of them is just a transistor to circuit ground through the ground pin of the IC. So they can sync current. And then you remember we look back at the power supply. We had this 100-volt pulsing high voltage power supply, and that is applied up here, and it goes into each of the Nixie tubes through a 10K resistor. That's a current limiting and voltage dropping resistor, but primarily it's there for current limiting. So let's say that this particular latch chip, memory chip, has a BCD code coming out that says 4. This decoder chip transfers that to turning on the fourth output. That's this one here. It doesn't say it here, but it's the one that connects to the number 4 in the Nixie tube. So now there's a path for the 100 volts to send current through this resistor from the anode to the number 4 cathode of the Nixie tube, through the internal transistor, and then to circuit ground. So we have a current path that will illuminate the number 4 in the Nixie tube. And if we had a different BCD code down here, then a different one of these would turn on and allow current to flow from the anode to a different cathode, thereby lighting up a different numeral. And that's all there is to that. Now each of these Nixie tubes has a decimal point on the right side and a decimal point on the left side. The left decimal points are not being used at all, and the right side decimal points are all brought out to pads on the circuit board. That's pin 13 here. They're all brought out, so pad on the circuit board 1, if you were to take that to circuit ground, then the decimal point on the least significant digit Nixie tube would light up. A pad called number 2, if you grounded that, then the decimal point on the right side of the next digit would light up, and so on. I think that Heathkit was planning on using this circuit board for more than one model of frequency counter, and so they just made it as flexible as possible. Made provisions for different decimal point arrangements. But in fact, none of these things are connected to anything in the IB-1102. The only one that doesn't come out to a pad, and notice it goes from 3 to 5 here, there is no 4, and that's because that one is internally connected down here, and guess what, it's 4. It's the same as these others, it's just shown lower down on the schematic in this instance because of where it's going in the circuit. That's going down here, it's going through another resistor, and then it's going to ground. So this big long path down here is just saying, hey, this is brought to ground, and because it's actually wired to ground at the switch, they've drawn it all the way down here. When I redraw this, I may change that. Okay, is there anything else? Oh yes, overrange. If we count up such a high count that all of these 8 decade counters have counted up to 9 and then rolled over, so now it's going to try to roll over again, but there's not another decade counter. But we want to know that we rolled over the highest decade counter, so its output that would normally feed into another decade counter is instead fed into an IC which has a pair of flip-flops in it, each of them configured as a divide by 2. And essentially what this is doing is it's capturing that status. It's logging the fact that we overranged the highest decade counter. So it's captured that event as if it was the first stage of another decade counter. And then it's followed by the other flip-flop, which divides again. So if this first one is toggled twice, it's toggled on, then we overrange again, it's toggled off. That would reach over and toggle the second flip-flop. So you essentially have a divide by 2 or a divide by 4 with the two of those in series. And this is your divide by 2, this is your divide by 4, and they go into a pair of flip-flops in this IC, which are controlled by the transfer signal. So whatever signal's on here and here at the time of the transfer signal is latched into these two flip-flops, and their outputs are here and here. Well, again, this is part of Heathkit being flexible. The divide by 4 is not used at all. It's still happening in here, it's still going up to here, but we don't use the divide by 4 output. There's a place on the circuit board for a jumper, and there's a jumper here from the divide by 2, so you could move the jumper one way or the other and thereby drive this transistor off of the divide by 2 or the divide by 4. I'm guessing that maybe they were thinking they would have a version of this that might have an additional, I don't know what they were thinking. It's almost as if they were envisioning a number 1 in the highest position that could only be a 1, like they did on some of the other lower end products. I'm not sure what they were thinking. I can only guess. But anyway, this one is hardwired with the jumper, so it's only looking at the divide by 2, and all that's doing is logging that the main counter chain overranged. Then when we get the transfer signal, we lock that in, so this can be reset, and in fact, it is reset. The reset signal that does all the decade counters also has to reset this flip-flop, but because its logic is upside down, it has to be inverted by this IC, or by this transistor. It's normally held high. When you have a high going transfer pulse here, it drags it low, so this chip requires a low signal in order to do a clear. So that's what that transistor is doing. Okay, now, we had an overrange happen. It's in this latch, so it's being held even after the decade counters and things have been reset. That goes over and turns on this transistor, which provides a current path through the overrange lamp to circuit ground. So it's just acting as a current sink for this lamp, and it works like all the other ones. So the over lamp will light up. And that, my friends, is the whole circuit ad nauseum.